Hello, everybody, and welcome back. This is the final topic for Unit 8. And in this topic, we will be looking at pathogens and infectious disease. Our enduring understanding is that pollutants can have both direct and indirect impacts on the health of organisms, including humans. All right, so let's do a little terminology definition, right? So a pathogen is referring to bacteria, viruses, or protozoans that cause illness and are transmissible through what are called a variety of vectors. All right, and so the term vector in respect to diseases is any living agent that carries and transmits an infectious pathogen to another living organism. So two of the most common ways, although there are lots more, are through mosquitoes and tick bites, right? So we can transmit a pathogen from one organism to another. Mosquitoes and ticks, which are involved with, sucking blood or biting one organism, can then carry a pathogen from that organism to another one, right? So things like malaria, Lyme disease, etc. All right. So there are some important links between poverty and infectious disease. And so one of the things we have to understand is that less developed countries often suffer from lack of infrastructure to treat wastewater. So as we mentioned before, dysentery, for example, is almost always linked to untreated sewage entering local waterways. Okay. And also because they lack the infrastructure to clean water that's leaving the homes, they often also lack infrastructure to clean water or filter or purify water before it is brought into the home for drinking. All right. Likewise, household solid waste, so garbage and so on, can get out there and cause all kinds of havoc. So this picture that I chose here is an example of a community, right, in which they don't have, a way, or infrastructure or a system in place where they could put their waste into garbage cans, and those garbage cans collected once a week by waste disposal company and brought out to a landfill, right? The garbage they don't really have a good way of getting rid of it. All right. So combine those factors with also inadequate medical treatment options, lower access to vaccines, and so on. So the infectious disease transmission in our less developed world is much higher than our more developed world. All right. Now, geography plays an important role too. So some pathogens, for example, occur everywhere naturally. So like influenza, for example, while it does get flu season, that we often refer to as the winter time up here, a lot of it has to do with the fact that people are spending a lot more time indoors and in closer quarters with other people, right? But influenza is all over the world and isn't limited to like the tropical region, for example. Okay. Other pathogens like malaria and Zika, though, are much more common in tropical areas for a variety of reasons, but one of them is that they tend to thrive best in those warmer and more moist conditions. All right. Now, that being said, when we factor in climate change, as subtropical regions become more tropical-like over time with the warming surface, right? Those tropic regions are migrating further north and south from the equator, and therefore so are many of those tropical diseases. All right. Now, couple that with globalization, both of travel, so people traveling around the world frequently, but also globalization of our economy. People and goods are moving from one continent to another. So areas that would normally be geographically isolated from other areas, so maybe even somewhere like Hawaii, right? Hawaii would geographically be very well protected from something like the coronavirus pandemic, right? If it weren't for the fact that lots of people travel to Hawaii for vacation and to visit and so on. All right, so because of this globalization, pandemics like the coronavirus pandemic are possible because people are moving all over the world, goods are moving all over the world, and therefore most of our what would normally be called epidemics, which will really tend to only affect one area, have become global pandemics, in which case they affect all areas. All right. So, which takes us right to our terminology. A pandemic is a global infection. Usually, we're talking about the introduction of a new bacteria or virus for which there isn't already a built up immunity. All right. Versus an epidemic, which would be a sudden outbreak, but only kind of constrained to a certain geographical area. Right. So, the Ebola outbreak of a few years ago, for example, would have been more of an epidemic issue, even though with globalization there is a possibility of those things. Ebola does thrive more in those tropical regions. This is much less of a problem in other parts of the world. Okay, so when we want to model and predict disease spread, right? So in the case of like a pandemic, for example, how can we go about trying to figure out where a disease will go and also how quickly it is likely to spread? Now, it's a very complicated business because there's all kinds of variables that come into play that actually impact this. So, what is the natural immunity like in that population already? What sort of access to medical care do they have? Do they have an ability, like a pandemic response team, for example, to shut things down and spread and isolate people from others to help prevent spread? So there's a ton of variables involved there, right? But when they are trying to predict how quickly a virus or other disease agent might spread, they use mathematical modeling. And we actually know some of the math involved with it, although it's far more complicated than I'll show you guys here, right? But ultimately, it comes down to an R value. R value kind of almost being like a rate, like we've used in population growth in the past, right? So in this case, the R T value is like a reproductive value of the virus, right? But really, it's referring to how many people. So if you have one infected individual, right, the value that's given to R is an indicator of how many other people are likely to be infected by that one individual. Okay, so if we had an R2 value, for example, that just means that one infected person is likely to spread it to two others, and then each of those would spread it to two others, and so on, right? So the R value indicates an exponential growth in the spread of a pathogen, right? And the larger that R value, the steeper that curve will be earlier on. Okay. Now, the other thing to consider that sort of complicates this is the fact that the reproductive value of a pathogen is going to vary from one place to the next. Part of that, again, is what sort of access do people have to medical care? How is the population vaccinated, right? What's the population density? And other existing comorbidity factors that might accompany that R value, right? But if we can estimate an R value, we can then predict how quickly that will spread. So in the case of the Omicron variant that we're just seeing the tail end of in parts of the world, right? In the UK specifically, based on their level of immunity already present, right? Their population density and so on. They estimated that the Omicron R value was 3.7. So basically, again, that would mean if we had one person infected, they would spread it to about 4 people, 3.7 people on average, right? So when you multiply that out, okay? So what we can do then is if we know that R value, like how likely is one person to spread it to other people and how many other people, right? We can begin doing some estimations of how quickly a variant will spread. Now, as you guys all know, Omicron luckily wasn't nearly as dangerous in terms of how sick people got with that variant, but it was much, much more transmissible than previous variants, partly because the vaccine didn't do a great job at preventing transmission. It did a great job of preventing severe illness, but not such a great job of preventing infection and transmission. All right. So with that super high R value of 3.7, right, we could estimate, let's say we started with just a single person infected, right? Okay. And that one person, again, they're not going to spread it to 3.7 people immediately. It's probably going to happen over about a 10-day period. And then each of those people would spread it to another 3.7 on average over another 10-day period. Okay, that was approximately the amount of time they were ballparking for how long people would be contagious. Okay, but again, the 10-day period varied based on variant and from person to person. But a person was likely contagious for up to 10 days. And over that 10-day period, for the Omicron variant in the UK, they were likely to pass it on to another 3.7 people on average. All right, so we can apply just a quick mathematical model to try to figure out, right, how many people would be infected after 30 days if that 3.7 R value came to be. All right. And we can use this familiar equation that we learned back in Unit 3 to estimate that. Right. So in this case, let's say our PO, our original population, this would be the one person that was infected. All right. We'll take that 1 times our E value, which is about 2.71, I believe. All right. To the RT. So R in this case is going to be 3.7. Right. And T is not going to be 30 days, right? Because we have the fact that one person over about a 10-day time period will affect 3.7 people. They're not going to affect 3.7 people in just one day. Okay, so for T in this case, I'm going to go 30 over 10. All right, or 3. So I go 1 times E to the 3.7 times 30 over 10. Okay, I'm punching numbers on my calculator. Okay, that so this will be about 11.1. So 1 times e to the 11.1 gives us about 66,171 people infected. Okay, so a single person infected with the Omicron variant after 1 month's time could result in about 66,000 people being infected with an R value of 3.7. So super contagious strain of coronavirus. And that's why we saw that huge spike. Now, the thing is, if we did that over a 2-month period, right, we end up with something like over 4 billion people infected. Now, there's a couple things that go on that prevent that from basically ended up at everybody within, just like 2.5 months, right? One of them is that 3.7 value applied to the UK specifically and their population density, right? 2, we had people exercising things like social distancing and mask wearing, right? 3, we started getting immunity, right? So again, even if you're vaccinated, plus you were already infected with the Omicron variant, you were much less likely to be reinfected. And so as we start building in immunity and other measures like vaccines into place, right, that begins to shift that 3.7 number down. So really, I'm just kind of illustrating how quickly diseases can spread in an uninfected population and with no immunity whatsoever, right? But as immunity builds up over time, and people and vaccines are available and other measures are taken, we can reduce that number quite a bit. All right. So estimating the spread of a disease is very complex, right? But we can model it mathematically just to kind of get a ballpark figure for how quickly it can spread. Now in class, next time I see you guys, we'll spend a little time talking about other diseases that College Board wants you guys to know about, but we'll just kind of do that stuff in class. As for now, let's sign out, and I will see you later.